Okay, 13 diplomas, welcome back to scholarship lesson 6. This is part C. So we just talked about what was happening in the first titration, that VO2 plus was being reduced by SO2 to something, we don't know what it is. That something gets oxidized back to VO2 plus and MnO4 minus gets reduced. And they gave you enough information to work out the number of moles of VO2 plus and the number of moles of MnO4 minus. Now, a similarity that you'll see is from this question and one we did previously last lesson, where we now need to work out the ratio between these two numbers of moles by dividing by the smallest number. Now, once we've got the ratio, what that actually tells us is actually the electron transfer that's in this reaction, which is really useful. So you can compare the number of moles in a redox reaction to the number of electrons transferred. So this here is your MnO4 minus. And this here is your vanadium species, that one that we don't know. Now, because it's 1 to 5, that means that that's effectively the numbers that you would times the reaction by, which means that you actually switch it round. So that means that the MnO4 minus has got a 5 electron and the vanadium one is a 1 electron. And that's what that means, because you'd have to times this reaction by 5 to make it equal the MnO4 minus reaction. Okay, so we know that MnO4 minus forms Mn2 plus, or sorry, well, we can guess it is now because we know it's a 5 electron transfer. And so therefore, the oxidation number of manganese in MnO4 minus is +7, and it goes to +2, which is a difference of 5. So the difference in oxidation number also equals the electrons. So it's a 5 gain electron transfer. So with that in mind, if we then work out the oxidation number of vanadium in VO2 plus, so it has to equal +1, and no one is oxygen and there are 2, so -2 times 2 is -4. So what plus V here would equal +1, and the answer has to be +5. So this vanadium has to be +5 -4, so it equals +1. So therefore, we need to work out which of those vanadium species is being produced. And we know that because it's a 1 electron transfer, and we also know that permanganate is getting reduced, which means the ON must go down, okay? And so with this one here, because we're thinking about what this original one, the VO2 plus, originally turned to something, okay, with SO2. So this was getting reduced. So this ON also has to go down. And so we know it has to go down by 1. Our options from the original question, because it gave you all the cell potentials in that original question where we ranked them, were VO2 plus, V3 plus, and V2 plus. These are easy because they're monatomic ions, so the oxidation number is just what it is. We've just worked out this one before, and VO2 plus has to equal +2. The known is oxygen. There's just one of them, so therefore this has to be +4 to equal +2. So therefore, in this first reaction, when SO2 reacts to SO4 2 minus for oxidation, the reduction equation is that VO2 plus is forming VO2 plus. And we know that because we worked out from the ratio that 1 electron was transferred. If 1 electron is transferred, then there is an oxidation number change of 1, and the oxidation number change of 1 is when this vanadium goes from +5 to +4. And so now we know that the blue species is this VO2 plus. I hope that makes sense. And here is the balanced equation of what's happening. So VO2, this one here, VO2 to VO2 plus. So this is going backwards in this case. Yeah. Okay, so what actually happened, just in case you didn't get it, the SO2 was oxidized to SO4. The VO2 plus was reduced to VO2 plus. The VO2 plus was then oxidized back to VO2 plus, and MnO4 minus was reduced. So I hope that makes sense. So the second titration, it said another 25 ml portion of the same ammonium vanadate solution was shaken with a zinc amalgamum to give a violet coloured solution. So this is a different one now, so a different vanadium species. This solution was titrated under inert atmosphere with KMnO4 solution. Inert atmosphere means that there's no oxygen present, and this many moles was required to reach the end point. Okay, so what we do here is the zinc amalgamum is like a mixture of zinc and something else to make it more stable. You can effectively just assume it's going to be zinc in its normal state. A bit mean to put that there, I think. So we know that we've got VO2 plus in our ammonium vanadate solution. Okay, so what's happening here is that zinc is getting oxidized to zinc 2 plus, and that vanadium species, VO2 plus, is getting reduced to something. We don't know what. That something is then going back to VO2 plus, and MnO4 minus is getting reduced to Mn2 plus. Okay, so this one is oxidation, this one's reduction, this one's oxidation, and this one's reduction. So hopefully that makes sense. And just like before, they've given you a volume and a conc, so we know the number of moles of VO2 plus, and a volume and a conc, so we know the number of moles of permanganate. So what we can do now is carry on, do the ratio. So we divide by the smallest number. Now when you do this, this is a little bit different, okay, because you end up with a partial number. So you can't have that. So you need to get rid of that partial number. And if we times them both by 3, you'll get whole numbers, and it's a 3:5 ratio. Now remember, you kind of switch where these belong. So this 5 goes here, meaning a 5 electron transfer, and this one here meaning a 3 electron transfer. So I hope that makes sense, okay? These are effectively the numbers that you would times the reaction by to these numbers here. So you'd times MnO4 minus by 3 to get the same number of electrons as the vanadium one, which you'd times by 5. And if you have to times this one by 3 and this one by 5, it's because this one's got 5 electrons and this one's got 3. So I hope that makes sense, that the 3 electrons are transferred in vanadium and 5 electrons in permanganate. We know permanganate's getting reduced to Mn2 plus, which is the 5 electron transfer, and that means a decrease of oxidation number of 5, and a 3 electron transfer in the vanadium. So we know we're starting with this one, which has an oxidation number of plus 5. So how can we get a difference of 3? And the answer is it has to be vanadium 2 plus. So in the reaction of permanganate and vanadium, we know that the oxidation number has to be different by 3 because there has to be a 3 electron transfer. And if you balance this half equation, in the second part, the permanganate is getting reduced to manganese and the V2 plus is getting oxidized back to VO2 plus. So let's just balance that. So you've got to add 2 waters to balance the O. You then add 4 H pluses, and then you've got to balance the charge. So 2 plus on the left-hand side, 5 plus on the right-hand side. So you add 3 electrons, and 3 electrons matches that. So we know we're correct. And so we've worked out what that violet coloured species was. It's VO2 plus. So just remember, this was actually the second part of the question. The first part was that the zinc got oxidized to zinc 2 plus, and the VO2 plus was therefore getting reduced to V2 plus. And then the second part was the V2 plus was getting oxidized to VO2 plus, and the MnO4 minus was getting reduced. Okay, so now we've got to link all that to the reduction potentials. They gave these reduction potentials in part A, and I've just put them here to make it a bit clearer. So we've got to rank these reduction potentials a little bit. So effectively we know because VO2 plus was reduced to VO2 plus and not V3 plus, it didn't continue to V3 plus in the first titration. So that means that SO2 has to have an E0 value in between these two here, so that the reduction stopped here. Because if SO2 had an E0 value below this one, that means that both of these reactions with vanadium, this one and this one, would produce a positive cell potential. And so you would end up with V3 plus being produced. But that didn't happen. We only had VO2 plus being produced, which tells us that the E0 had to be slightly higher than the second one here. Slightly higher than 0.34. The next part was that where does zinc lie in all this? Well, we know that when VO2 plus was reacted, it went all the way to V2 plus, which means that zinc must have a cell potential lower than this, because the lowest cell potential gets oxidized and zinc got oxidized. So zinc has to have a lower cell potential than 0.26, and SO2 must have a cell potential between 0.99 and 0.34. Hope that makes sense. Let me know if it doesn't. The final part here says an alternative to using an inert atmosphere, so no oxygen for the second titration, is to quickly decant the violet solution is the V2+, into excess ammonium vanadate, and so that's your VO2+, and then do the titration. So they're saying that instead of having no oxygen, you can actually react these two together and then do the titration. So explain how this is useful and what's happening. So what's happening in this one is that the reason why the alternative method exists is because, or why you need an inert atmosphere, I should say, is VO2+ that gets produced from VO2+, is actually very unstable, and it easily gets oxidized by oxygen in the atmosphere, and that's why we need the inert atmosphere. So an alternative to keeping the atmosphere away, which in reality means that you'd have to be in a specific type of laboratory to do that, a specific fume hood or whatever, is to oxidize the V2+ in a controlled way by reacting it with VO2+. This is probably the hardest part of the whole question, so I hope you managed to follow along with me. So I don't know many kids that would have got this, to be honest, but I'm going to show you now why. So if you react V2+ with excess VO2+, which it said in the question, VO2+ would get reduced to V3+. Okay, so this VO2+ would get reduced all the way to this V3+. And the V2+ would get oxidized to V3+, and this would go here. And we know that because if you work out the cell potentials, both of these become positive. And if they're both positive, both of those reactions will exist. And we also proved that earlier on because we said that V3+ was the most stable. So we've already actually discussed that, and you can look back before if you want to. And so the reason why this is possible is because VO2+ has a much higher cell potential, so will be reduced, and V2+ has a lower one, so would get oxidized. So we know that V2+ will only get oxidized to V3+ and not the other two, because it could get oxidized to the other two, but not in this situation because we're actually adding this in excess, the VO2+ in excess. And because this has got the highest reduction potential, it would always get reduced. So if any of this V2+ got oxidized, it would immediately get reduced by the excess VO2+. I hope that makes sense. So the V2+ gets oxidized to V3+, and the VO2 gets reduced to V3+, and here's your overall equation. So this is a nice stable way of having it, and then what would then happen is that the V3+ would then get oxidized back to VO2+, and the MnO4- would get reduced. So this is another way this titration could have occurred. Okay, now the last part of the question, it said, well, why is it the same amount of MnO4- required if you're doing a different method? And if you look here, if we're doing this V2+ and reacting it with VO2+ to produce V3+, you'll see that one of these, three of these V3+, are produced in this reaction here. And so this reaction here, which you can see, is a 2-electron transfer. The one that gets, when the V3+ goes back to VO2+, is got 2 electrons. So if you'd produced 3 of these by doing the first stability part, then you would need 3 of these, which would make this a 6-electron transfer. So that would end up being 6 electrons. And if we look at the example when we had the zinc reacting, with the zinc here, you can see that 2 of the V3+ are produced. And so that's 2, and that would actually be 6 electrons. And so because the same number of electrons are transferred in each titration, it's the same volume. Okay, team, and here are your 2 homework questions. So you can pause and have a look, and pause and have a look. I've loaded these both onto the OneNote and put them onto Teams. And that is lesson 6. Very well done, team. I'll see you on Monday at 8 a.m.